All right, we're here for Honors Physics, free fall questions and problems, looking at problem number 5, which says, draw graphs of the speed and the distance fallen as a function of time for an object falling under the influence of gravity from time is 0 to time is 5 seconds. Ignore air resistance and assume that V naught is 0. How precise do these graphs need to be? Are we looking for quantitatively accurate or just qualitatively accurate? We can probably do it kind of semi-quantitatively without too much effort. So let's go ahead and give this a try. Let's look at, now you notice that the graphs they want are speed and distance as a function of time. And you say, remember what's special about speed and distance? They're scalars. They don't have a direction. They're always going to be positive values. So I don't need to draw quadrant 1 and quadrant 4 on my graph. I can get away with just showing the first quadrant on my graphs. That's kind of nice. It's kind of nice. I like that. So here we go. So our first graph, there we go. Okay. So this is going to be speed in meters per second, perhaps, if I'm going to do it quantitatively. And this will be time in seconds. All right. And we'll go ahead and we'll mark this off. 1, 2, 3, 4, 5 seconds. Yeah. Okay. 0. Spacing is not quite right. So here we go. And we'll also do a graph. And now I'm going to make, oh, man. I normally like to put like position and then velocity and then acceleration going down my sheet this way. I just always do it the same way, and then I can remember the relationships between them and helps keep me from making mistakes. But this is going to be backwards. I'm going to have speed above distance because they wanted me to do it in that order. That's annoying. Oh, well, that's okay. That's okay. If I was to do this again, I would flip that. All right, here we go. Now I'd like these to line up so that I can do comparisons, you know what I mean? Between my two graphs, easier. Right, 1, 2, 3, 4, 5 seconds. Because this time axis, it really is the same as the other one. We're looking at the same amount of time, but we're looking at distances instead of speeds. Distance in meters. There we go. All right. So we're looking at something falling. Now, if we're falling, right, we are going to presume that we start with a velocity of 0. So we're going to start with the speed of 0. So our speed graph will start here at the origin at time 0 at speed 0. And as we fall, we're going to get faster and faster. Again, speeds are all going to be positive, even though we're going downward, because that's the way speed is. It doesn't show direction. It's always a positive answer. Now, what we know is, we know that for anything that's falling, here we go, we know that initial velocity is 0 because we're just starting from rest, I'm assuming. And we also know that the acceleration is negative 9.8 meters per second squared. Now what that means is every second we subtract 9.8 from our velocity, but we're using speed. And so we're not worrying so much about that 9.8. We're going to be going down, right? This object's going to be falling, and the acceleration is down. So we're going to be getting faster. And so because we're doing a graph of speed, I'm like doing the absolute value of it. So it's going to be getting farther away from 0 as it gets larger. Does that make sense? Okay, so we're going to be getting a faster and faster. We've got to be getting farther away from 0 to get faster. So, and the thing about this is acceleration on a VT graph is the slope, right? It will also be the slope here, okay? Except that it's going to be absolute value because of the way we're doing speed. That's annoying. So we're going to draw a line that has a slope of 9.8. All right. So now, fortunately, we haven't labeled this axis yet. Aha. So I'm going to draw my line and then later on label this so that it looks right. So we have a slope of 9.8 as we go faster and faster and faster as we fall. Oh, actually, they say right there, assume V naught is 0. So that's it, right? Until it hits the ground, right? So for the first 5 seconds, I should have stopped my graph there. That's what it looks like. Now, this 9.8 means every second we are going to subtract 9.8 from our velocity. So 9.8, we want to go for 5 seconds. So 9.8, 19.6, 27.4, 36.2, 47. Is that right? Wait, 5 times 9.8, that'd be 5 times 9 is 45, and 5 times 8 is 4. So yeah, 49. So our final velocity here at 5 seconds is going to be 40. Well, our velocity will be negative 49, but our speed will be positive 49. So we know that's going to be 49 meters per second. All right. Okay. Are you okay with how I did that? I hope so. Every second we're subtracting 9.8 from our velocity. We're starting at 0. 5 seconds later, 5 9.8 gives me negative 49. Okay, there we go. So that's that graph. Okay, beautiful, beautiful. Let's go to the distance graph. You're like, well, distance is going to be trickier. Okay, so distance is, again, kind of like displacement. It answers the question how far, except that we're doing absolute value, and we only care about the total length traveled. Now, in this case, we're not going back and forth, so the size of the displacement will be the same as the size of the distance. Our displacement's actually in the negative direction in this case. We're just going to flip the sign, make it positive in this case. We can do that for distance fallen. So taking a look at this, if we, so we're going to say that we're going to start at position 0, then our graph will start here. All right, had a little quick break there to see what my son Andrew needed. So here we are. So we have the speed time graph done. Now we're looking at distance time. We talked about the fact that distance is, in this case, since we're just going in one direction the whole time, the distance is just going to be the absolute value of the displacement. So what I'm going to do, we're going to assume that we start at position 0. So our graph starts from 0 there, 0, 0. And again, we're just going to take the absolute value of the displacement. So we're going to have all positive values. So we only need quadrant 1. So what I might do is, let's find like where this graph ends, okay? Find the distance at the end. So I'm going to go ahead, I'm going to solve for the displacement at 5 seconds, right? And I'm going to go ahead and use A, V naught, V. We know the T is 5 seconds. So you say, hey, we got lots of good values to work with here. I think I'm just going to use delta x is v naught t plus 1/2 at squared for this one. We know the initial velocity is actually 0. We're starting from rest. And so my displacement at 5 seconds is just going to be 1/2. My acceleration is negative 9.8. And then times 5 seconds squared. And so punching in my calculator really quickly, I can see that I'm going to get 122.5 meters. It would be a negative 122.5 meters for the displacement. But again, I'm just going to flip the sign on that because we're just going all in one. We're actually just going in the negative direction the whole time. I can just flip the sign and get the distance. So 122.5 is where we want to end. So I might just go ahead and we'll put a little dot there and track over and say that's 122.5. And we're not going to worry about being hyper accurate with this graph. But here's the thing. We know that if I had a position versus time graph, that the slope of a position time is the velocity. And in this case, the slope of the distance time is going to be our speed. So we recognize that the speed at the end here is 49. That means we want the slope at the end to be 49. It's going to be really steep. At the start, the velocity is 0. So the slope here is going to be 0. A 0 slope is like no rise for your run, yeah? Rise over run is slope, and that's 0. So it's like I'm going to have to go from horizontal to really steep, a slope of 49 for everyone. So this thing's going to be going really steep by the end. So it's going to be a curve like so. How precise do we need to have that curve? Honestly, for this course, we're not looking for it to be really precise here. We're just looking to have a curve that goes from starting off flat to pretty steep here. Okay, if you wanted to be like even more precise, we could pick a value in the middle, repeat this calculation, maybe for the 3 second mark, maybe put 3 in there and have half a negative 9.8 times 3 squared, right? And have, and we'd find that we, at 3 seconds, we're at 44.1 when we do that calculation. And so you'd be like, okay, 44.1, that's about a third of the way up here, right? Yeah, roughly. So you're like, well, gosh, when I'm at 3 seconds, I'm somewhere like here. So you can see that curve is going to steep like this. So I might do a curve something like this. Okay. So that's what my graph looks like, my distance versus time for a falling object. And you say, I can see I'm getting steeper and steeper and steeper. It's changing all the time, the steepness. That's because my speed is changing all the time because we're accelerating, okay, as it gets steeper, steeper, steeper. And so I think that's good enough for us. All right. No need to be super precise with this. We could go through and punch a whole bunch more values in and get more dots to kind of put this in, but I think that's enough for us. All right, problem 5.